Hi students, in this session we will discuss about transform impedance and transform admittance circuit of capacitor. In the previous classes we have studied about the transform domain circuit for the capacitor, and from that circuit we are deriving the transform impedance and transform admittance circuit for the capacitor. Suppose we are having a capacitor having a value capacitance C, and in that case we know that the current through the capacitor will have the equation IC of t is equal to C into dVc of t divided by dt. That you might have know about this equation because it is the basic equation for the capacitor. And next, similarly, we can find the voltage across a capacitor as Vc of t equal to 1 by C into integral minus infinity to t IC of t into dt. These are the two basic equations that you should by heart, and it is a very important equation, and this is the equation for the capacitor. So, in order to find the transform equations, we have to take the Laplace transform of the equation. See, here we are taking the voltage equation for the capacitor, that is Vc of t, and we are taking the Laplace transform of this equation so that we will get the equation in S domain, right? This is a time domain equation, that means voltages and currents vary in accordance with the time. When we are transforming into the S domain equation, we will get the equations in terms of S. See, actually we are transforming the time domain to S domain in order to convert the integral form into algebraic form. See, these equations contains a differential term, this equation contains integral term. So it will be very difficult to analyze the circuit using this differentiation and integration. That is why we are going for S domain approach. In S domain approach, the integration and derivation will convert it into algebraic equations. So when we are taking the Laplace transform of Vc of t, we will get Vc of s. Similarly, integral has got the Laplace transform. We know that if there is a function f of t, its integration has got a Laplace transform f of s by s. That is why here instead of IC of t, IC of s by s comes, plus then we will put the initial condition. Initial condition is IC of 0 plus divided by s. Instead of IC of 0 plus, we can write the charge on the capacitor, that is Q of 0 plus divided by s. So we will get the S domain equation as Vc of s equal to 1 by C is a constant, so we can take it outside, that is 1 by z into, instead of integral IC of t, we will get IC of s divided by s plus Q of 0 plus divided by s. So this is the Laplace transformed equation for this voltage in the case of capacitor. So this is the, we can say that it is equivalent transform equations for the voltage expression. And we can rearrange, see, we can rearrange this equation as, see here Q of 0, there is a term Q of 0 by C, which is equal to Vc of 0 plus, and that is initial voltage across the capacitor. Also, when we are rearranging the equation, we will get 1 by Cs into Ic of s equal to Vc of s minus Vc of 0 plus divided by s. See here, we are taking this Ic of s terms in the left side and taking Vc of s to the right side. That is why we are getting this equation. So considering the total transform voltage across the capacitor as V1 of s, you can see if we are taking V1 of s is equal to Vc of s minus Vc of 0 plus divided by s, that is the total voltage. So we are considering the total transform voltage across the capacitor as V1 of s. So we can write V1 of s will be equal to this quantity. So this equation, that is equation number 1528, will become 1 by Cs into Ic of s will be equal to V1 of s. In this case, when we are taking the fraction V1 of s by Ic of s, that will be equal to 1 by Cs. But you know that V1 of s by Ic of s is nothing. It is nothing but it is impedance, right? Voltage divided by current will give the impedance. Therefore, the transform impedance of the capacitor is the ratio of the transform voltage V1 of s to the transform current Ic of s. So the transform impedance will be equal to V1 of s divided by Ic of s, that will be equal to 1 by Cs. That is an important relation, you should remember it, okay? So we can draw the time domain circuit and a transform domain circuit. First, there is a capacitor C, and the capacitance, initial capacitance or voltage across this capacitor is Vc of 0 plus, and the voltage across the capacitor is the time domain voltage is Vc of t, and corresponding current is Ic of t. This is the time domain representation. So for 15.8a shows the time domain representation of the capacitor C with the initial voltage Vc of 0 plus across it. And see, next we want to draw the transformed circuit for the capacitor. You know that actually this is the voltage equation, and in this you can see that voltage will be equal to Ic of s by 1 by Cs into Q of 0 plus divided by S. So this is the voltage equation. So one voltage is equal to the sum of these two voltages, right? So first is the term Ic containing Ic of s divided by 1 by Cs. So this is actually the impedance term. So we can write it, we can represent it by a rectangle. So first term in the diagram will be 1 by Cs, and its impedance is set C of s. And you can also see next term is Q of 0 plus divided by S, Q of 0 plus divided by Cs. That is the second term. So that is actually a voltage source. Therefore we can write it as Vc of 0 plus divided by S. That is a voltage source. So in the case of a capacitor, transform domain circuit can be drawn as a series combination of an initial voltage source and also the impedance set C of S. Similarly, we can take the current equation. See, here there is a current equation Ic of t equal to C into dVc of t divided by dt. If we are taking the Laplace transform of this equation, we will get Ic of s. That will be equal to Ic of s is equal to C into S into Vc of s minus Vc of 0. So we can write Ic of s is equal to C into S into Vc of s minus Vc of 0 plus. That is a transform equation for the current in the case of capacitor. And if we are rearranging this equation by taking this term to left side and this term to right side, we will get C into S into Vc of s equal to Ic of s plus C into Vc of 0 plus. So here, considering the transform current through Yc of s as I1 of s, then see this is the current, and we can write it as this is the current. Therefore we can write it as C into S into Vc of s equal to I1 of s. See, this is a current equation. So we can write it as instead of the complete term, we can write it as I1 of s. So this equation will become Cs into Vc of s equal to I1 of s. And in this case, if we are taking the ratio I1 of s by Vc of s equal to C of s, that is equal to Cs. So you know that current divided by voltage gives the admittance. So we can, instead of I1 of s by Vc of s, we can write it as Yc of s, that is equal to Cs. So Cs is the quantity which gives the admittance. So we can draw the transform capacitor circuit in terms of the admittance as, see, we are actually utilizing this equation. See, actually utilizing this equation, that is current will be equal to sum of the two currents. So we can write actually this is a capacitor time domain circuit, that is capacitor C, initial charge Vc of 0 plus Vc of t is the time domain voltage and Ic of t is the time domain current. And we can replace this capacitor by the parallel combination of two values of, that is Cs, which is a admittance, and the other one is C into C. Here C into, that other one is C into Vc of 0 plus C. This is the current equation. So each and every term will be a current term. So this will represent a parallel combination of currents. So first part contains Cs, which is the admittance term, and second part is another current source with the initial charge on it, that is Vc of 0 plus. Since minus sign is there, so the current direction will be upwards. So this is the admittance, transform admittance representation of the capacitor circuit, that is 15.9 gives the transform representation of the same capacitor in terms of admittance. So in the case of capacitor, there are two representations, that is one by using transform impedance and other by using transform admittance circuit. So you should remember these two circuits. It will be useful for solving problems. Next, if we are considering the series and parallel combination of elements, suppose here we are not analyzing it, actually we are giving an overview of that, that is different components are R1, R2, L1, L2, C1, C2. These are connected in series. Then corresponding transform representation circuit will contain series combination of their impedances, that is ZR1, ZR2, ZL1, ZL2, ZC1, ZC2. That will be the representation. Similarly, if we are taking parallel combination of circuit elements such as resistance, when we are taking G1, G2, L1, L2, C1, C2, etc. are connected in parallel, then the corresponding transform representation of the parallel network contains admittances. The admittances are YG1, YG2, YL1, YL2, YC1, YC2, etc. So this is all about the transform domain circuit representation for the different circuit components such as capacitor, inductor, resistor, etc. In the next session we can do a problem. Thank you.